Okay, let's go ahead and get started. We've got almost a full house. We are going to take a look at the endocrine system today. This is the first of the labs. A little bit about the AP2 lab. All your content is found in eLearn as far as PowerPoints and PDF files. And again, I recommend that you print out the PDF file. I've set them up 4 PowerPoint slides to a page, so you can use those to take notes on. Plus, they're going to be good for review for your lab test. Some changes from AP1 to AP2. There are only 3 labs. Three lab exams instead of 4. Each one's worth 100 points, and for a total of 300. And that's all the points available. So you need to do your best. The first lab will cover endocrine. Next week will be reproduction. The third lab will be blood. I know it doesn't seem to make any kind of good connection, but just the way it breaks out. So we'll do endocrine this week, reproduction and pregnancy next week, and then the week after Labor Day. I think that works out right. We do blood, and then we'll have our test will open up. The second unit is on heart and blood vessels and assessments and the lymphatic system. And then the third section is on digestive and respiration and urinary systems. So we should, if you've taken a look at the lab schedule, which is found in the eLearn content, I'm anticipating being done before Thanksgiving. We do have one advantage with these online classes is we can have the exams online too. And that means we don't have to take a day out of the schedule to actually give the exam in class. When we finally get back to on-ground exams, I don't know how I'm going to react to that, because I'll have to keep my pace a little faster. But we will be done earlier than you know. The AP2 labs always get done early anyway, because we tend to cover all the content at least a week or 2 earlier than the AP1 labs. This year, this fall, I'm anticipating, like I said, out before Thanksgiving. So, and let's see what else. We will adhere to the lab schedule. Lab schedule is while we don't adhere to a test schedule in AP1 in AP2 lecture. In lab, we have a pretty definite schedule, and that's a real throwback to when we were working on the ground. But it will be fine, because we'll cover 1 unit per week, and we'll have a test after 3 units, and that'll cover everything, in that unit. And then, again, there is no final exam, but so it's as much of a practical exam as I can make it while still being online. So let's see. Same grading scale, 90 to 100 today, and so on. Remember that your lab grade doesn't have any real impact on your admission into any of the healthcare programs. The only thing your lab grade does is contribute in a very, very small way to your overall GPA. And that contributes to your overall point basis. So I would not spend, if it comes down to between lecture and lab, the choice has always got to be lecture, because no one's gonna ding you for getting into a nursing program or something, or respiratory therapy or radiography or anything if you got an A in lecture and a C in lab. That's not gonna ding you. So make sure your focus stays on lecture. So, not to talk down to the lab. Lab's important, but as far as earning those points for whatever program you're looking at, just keep your perspective. And if anybody wants to know more about the, I have the information on nursing somewhere in my office. I moved my office over the summer, so I don't know exactly where it is, but I do have it. So if anybody's interested in nursing and wants to know exactly where the points are earned from, let me know and I'll be glad to come on campus and meet with you. So anybody have any questions about this? Yes, lab will be posted on YouTube also. It'll have its own, I'll have them all organized by block so you can watch them there. Because again, things are going to get in the way. We all know that. If you had told me in March of 2020 that I would not be in the classroom again until probably January of 2022, I would have said that's ridiculous. So, but yes, I will have everything on YouTube for you so you can go look at that. Because like I said, if you miss a lab, it's not the end of the world. Just make it up by watching the YouTube video. Things are going to happen. Cars break down, computers die, Wi-Fi gets lost, people get sick. So whatever. And it's all, I'm very, very flexible. Those of you that had me before know how I'm very, very flexible. So the other thing I'll tell you is that these labs usually don't last very long either. I know I'm talking a lot right now, but we'll be done by 2 o'clock. And that's going to apply in most cases. There will be only a couple labs that will go long to get them in. But even when we were on the ground, it would take a lot to stretch it past 2 o'clock because there just isn't that much to cover in some of these labs. So just will the link to YouTube be posted in eLearn? Yes, and I'll give you the name of my my YouTube channel also. So so you'll be able to get to it very easily. I just haven't set it up yet because I haven't been to YouTube yet. I've only just now started. It takes a couple steps to take the Zoom video and convert it into something for YouTube. But by the end of the day, you should be able to see the links and go back and look at the videos. So, okay, good questions. Thank you. Any other things? Comments, questions? Anything to keep me from babbling? Oh, go ahead.
My internet did glitch on lecture. You said OpenStax would be our book?
Yes, OpenStax is the book. It's free. You can download it as a PDF or you can just view it as an ebook. If you'd like to have something tactile to touch, I'd recommend go buying a used textbook at an old bookstore. But the PDF, you can always download the PDF file for the chapters we're addressing from OpenStax.
Okay, thank you.
Certainly. Okay, so now I'm going to go ahead and see if I can't get us into this. And here we go. Okay. You should all see the screen that says AP2 Lab, the endocrine system. Okay. So this is a torso model that we have in the lab. And if you're on campus, feel free to either ask to go into the lab and take a look at some of these. They're going to be as we start working through the lab, they're going to be sitting out in 217. And 217 is the classroom we'd be using for lab and for lecture. And my office is in the back, and some days I'll be there and some days I'll be doing this from home like I am today. And but all the models are going to start showing up in 217. So if you want to come to campus and go in there and look at the models, just ask campus police to unlock the door or go into the office. They'll know that I've said it's okay. So anyway, this is the torso model, life-size torso model. And what you're seeing here is location of the thyroid gland. Now, the thyroid gland is located in the middle of our neck. If you can press against your throat gently, you come up from the, you can feel the top of the sternum, and you come up, you'll feel a little dimple in your neck. And that little dimple right above that is the location of the thyroid gland. That dimple is right there, and there's your thyroid gland. It's shaped sort of like a butterfly or an H. And I mean, it runs on both sides. And it has two lobes, and it's connected across by a structure called the isthmus. And it produces a structure known as thyroid globulin, which becomes thyroid hormone. It's filled with a series of bubbles called follicles, and it makes the thyroid globulin in here. And when the thyroid globulin combines with iodine, it becomes known as colloid, and colloid is what becomes thyroid hormone. Now, around these follicles are cells called parafollicular cells. Parafollicular cells make calcitonin. We talked about calcitonin before. Calcitonin is a bone-building hormone that comes into play if calcium levels in our blood get pretty high. Doesn't happen very often, so we don't use a lot of calcitonin. In fact, calcitonin is not a major player. So what are we looking at? Well, here is our thyroid gland right there. A lobe here and a lobe here, and there's the isthmus in the middle. That little dimple I was talking about is located right here, and you can find your thyroid gland just above it there. Now, when I'm talking about colloids, these pink bubbles here contain colloid. These are follicles. These bubbles are called follicles. They're made by these cells around the outside edge, and those are called follicle cells. So the follicle cells make the follicle, and within the follicle contains this substance known as colloid. Colloid is the thyroid globulin precursor, half the precursor of thyroid hormone, and iodine, the other half. So when you have thyroid globulin, the protein thyroid globulin made by the follicle cells, combined with iodine from your diet, you get thyroid hormone. Why iodine? I don't know, but that's just what we require. So the follicle cells make the thyroid globulin. Iodine comes from our diet, and it combines to form inside here to make the colloid, which becomes thyroid hormone. Now, where do we get iodine in our diet? Well, number one location is salt. Most salt is iodized, meaning iodine's been added to it. And sea salt, for example, doesn't have iodine. We all like sea salt on things, on chocolate, for example. But if you ever look at a container of sea salt, there may be a notice on the print on the side of the container that says not a source of dietary iodine. That's how you know it's real sea salt, because sea salt, ocean salt, doesn't have iodine in it. But we get most of our iodine by way of our salt, and that iodine is necessary then to complete the production of thyroid hormone. This is a closer look at this. Now, this is a follicle right here. This great big thing here is a follicle. These are follicular cells on the outside of the follicle. Inside this follicle is colloid. The follicle cells make thyroid globulin, and that combines with iodine in here to make the colloid, and colloid is going to become thyroid hormone. Now these cells tucked away in clusters here, let's see, there's our thyroid gland, that's a follicle, that's a colloid, that contains the colloid. There are the follicular cells there. All those cells around the perimeter of each one of those follicles is a follicular cell. Each one's making thyroid globulin, and then that's combining with the iodine. This structure here, these are called parafollicular cells, and these cells produce calcitonin, but only when calcium levels are very high. Because calcitonin is used to stimulate osteoblast bone building activity. And we have osteoblasts and osteoclasts. Osteoblasts are the bone builders, and osteoclasts are the bone breakers or the bone destroyers. The parafollicular cells produce calcitonin, which stimulates osteoblast activity to incorporate excess calcium in the bone. Doesn't happen very often, if at all, because we're never usually going to be in a situation where we have excess calcium. We're nearly always going to be running a slight deficit on calcium, because calcitonin doesn't have a significant role to play in maintaining calcium levels. You know, as I say, calcium homeostasis. On the posterior surface of the thyroid gland are the parathyroids. There are 4 of them, about the size and shape of a raisin. They're going to secrete parathyroid hormone, which is the #1 hormone regulating calcium levels in the blood, because calcium levels are always going to dip. And so parathyroid hormone stimulates osteoclast activity, breaking down bone to release calcium. We're looking at the posterior surface of the thyroid gland, and here are the usually four parathyroid glands on the posterior surface. Again, about the size and shape of a raisin. Just for perspective there. And they're going to secrete parathyroid hormone. And the structure is different. And if you look over here, here's a colloid, or rather, here's a follicle filled with colloid. These are follicular cells around the edge here. These are parafollicular cells over here. You can always spot the parafollicular. So they're clustered in a group, and they're not surrounding a follicle. So this is a follicle filled with colloid. There are follicular cells. There's parafollicular cells. And over here, in a cluster of a lot of smaller cells, lots and lots of nuclei. These are the parafolliculars. These are the parathyroid gland cells over here. There's the parafolliculars over here. But these are the parathyroid glands. And this is a very good cross-section that covers it gives you the perspective of the thyroid gland on either side, with the parathyroid gland right there in the middle of the picture. Because over here these are follicle cells here all the way around. Here's a follicle filled with colloid. There's parafollicular cells there. And over here, this is the parathyroid gland. So, you can see how big it is compared to the rest of its overall size. Again, in gross anatomy, it is about the size and shape of a raisin. Thyroid gland, parathyroid in the middle. Chief cells are the primary cells. Chief cells are the chief cells in the parathyroid. Sorry, that I couldn't resist. chief cells are the primary cells that you find in the parathyroid gland. And again, parathyroid gland produces parathyroid hormone, which is the #1 regulator of calcium levels in the body. So we slide down, we can see the pancreas. So we got the thyroid gland. The thyroid gland is probably the largest of the true endocrine glands. It has nothing to do except secrete thyroid hormone and parathyroid hormone, well, thyroid hormone and calcitonin, and then we have the parathyroid hormone from the parathyroid glands. But it's the largest true pure endocrine gland because there's no other ductwork going on here. The pancreas is a large organ, as we see here. Pancreas is tucked up underneath the stomach. The stomach would be right on top of the pancreas. The stomach would be sitting here because there's the entrance to the small intestine right there. So the stomach would go from here up to here. Here's the end of the esophagus up here at the top. And the pancreas is underneath the stomach, tucked away to the left-hand side of the body, sort of butting up against the spleen. This purple speckled thing here is the spleen. The pancreas is a double action gland. It has a duct. This big white thing here is the pancreatic duct, because the pancreas releases enzymes for digestion of protein that dumps into the small intestine right in here. It also allows bile from the gallbladder to come down through that green duct here and also be discharged into the small intestine for breaking down fats. So there's the pancreas. Within the pancreas, for the endocrine function of it, there are clusters of cells. They're called pancreatic islets, known as the Islets of Langerhans. These little clusters are found throughout the pancreas, and it is the Islets of Langerhans that produce insulin, but also another hormone called glucagon. Insulin is released to lower blood glucose levels. Insulin, of course, will stimulate the production of carrier proteins in the cell membranes so that glucose can be absorbed. Well, it also produces another hormone called glucagon. Glucagon stimulates the release of glucose, sugar, from the liver, from the stored glycogen. So if our blood glucose levels get low, for example, if you skipped breakfast and lunch today, your blood sugar levels were down, your pancreas would be secreting glucagon to cause the liver to give up some glucose sugar so that your blood glucose levels, your blood sugar levels would stay constant. You may still feel uncomfortable and worn out or tired out, or just hungry if you skipped meals today, but your blood sugar levels would be high enough to keep your cells functioning. So there's our pancreas right there. There's the pancreatic duct in the middle. There's your small intestine here. There's your gallbladder tucked up underneath the liver. It dumps bile through the common bile duct into the pancreatic duct, and they all join together and come into the small intestine. The Islet of Langerhans, excuse me, looks like this. They are lighter staining clusters of cells inside the pancreas. The cells out here, the darker staining cells, are called the acini cells, and they produce the digestive enzymes. But these lighter cells are the Islets of Langerhans, and they produce both insulin and glucagon. So, and here's these are the acini cells out here. This is the this is an Islet of Langerhans here. Contained within the Islet of Langerhans are both the alpha cells and beta cells. The alpha cells make glucagon. The beta cells make insulin. So, but you can, when you look at a slide of this, it's very distinctive. You can see a definite change in the, you can see the cluster, and there's a very distinct region around that. So I guess that's where the term islets of Langerhans is probably the physiologist or anatomist that discovered them, and he said it probably looks like a little island. So it's probably where it came from. Anyway, this is a really bad picture. I promise not to use this picture on the lab exam, but even this, you can look at it and say, well, where's the area that looks different? Well, it's right here in the middle. This is the islets of Langerhans here. These are the Acini cells on the outside. Again, the pancreas, islets of Langerhans right there. I don't believe in having surprises on the lab exam. So, but this is what it would look like, and it's pretty distinctive. There are very few things that look like that, these islets anyway. So anyway, Acini cells out here, Islet of Langerhans, and we'll come back and talk about the Acini cells towards the end of the semester when we get into the digestive system. We'll be talking about how the pancreatic enzymes are made and released into the duodenum, the first part of the small intestine, to break down protein, and how the bile from the gallbladder is released into the small intestine to break down and chop up fats. So we'll come back to the pancreas again, probably in our last lab. Again, there are the Acini cells. So the again, yeah, this is a very good picture of Acini cells and Islet of Langerhans. This is the picture that always used to be used in the lab slides. So I've never liked it. So anyway, as far as testing goes, you'll see a well-defined islets of Langerhans. Okay. Now let's move on to the pituitary gland. Pituitary gland is the so-called master gland of the body. It releases 8 different hormones. It makes 6 of those hormones, and it stores 2 additional hormones. So it can release 8 different hormones. It has an anterior region and a posterior region. The anterior region is secretory, and as such, it stains darkly. The posterior region is storage only, and so it stains much lighter. And we use it in addition to anterior and posterior pituitary. We use 2 other terms. We use neurohypophysis and adenohypophysis. The neurohypophysis is the posterior pituitary, and the adenohypophysis is the anterior pituitary. Now, as I said, the area that stains dark is the secretory area. The area that stains light is just the storage area. The adenohypophysis, the anterior pituitary, makes and releases 6 different hormones. It's still under the direction of the hypothalamus. The neurohypophysis only stores 2 hormones. Those hormones are made in the hypothalamus, transported to the posterior pituitary, and stored there. And that's all that they do. They get released when they're needed, but they're not made there. They're not made in this region. The neurohypophysis or posterior pituitary. So the dark area is the anterior region. The light area is the storage area, is the posterior region. And we're going to see that a lot when we talk about secretory cells. They're always going to stain darker because they're much more active in secreting. So Okay, now this is, again, the pituitary gland. This area over here is lighter than this area. This is the posterior pituitary right there, or the neurohypophysis. This is the adenohypophysis. It stains darker because these are secretory cells. These are just storage cells. Big difference here. So this is the anterior pituitary. This will produce 6 different hormones. This will release 2 hormones that it's storing that have already been made in the hypothalamus. Okay. Now these are the adrenal glands sitting on top of the kidneys. The kidneys, again, would typical kidney would fit in the palm of your hand. And I'll have to, I have some very nice models on the kidney. I'll see if I can't figure out a way I can show you the model on my hand before we start the lecture. But the kidneys are very small, and the adrenal glands are even smaller. So if the kidney is about, if our kidneys are about 3 inches long, the adrenal glands are only about 1/3 of that. So maybe 1 inch across or 1 inch high and maybe 2 inches across. But these are the adrenal glands. They sit on top of the kidneys. And the kidneys, of course, ride directly underneath our rib cage. In fact, they're right underneath our diaphragm in the back wall of the abdominal cavity, up very high. They have, so if you have a patient someday that comes in and they're holding their back right above their belt line, and they're saying, "My kidneys hurt." Well, that's not their kidneys. They might have a kidney stone, but it's likely it's muscle pain. Unless, of course, they have a really large kidney or they've had a kidney transplant or anything like that. But that's beside the point. We'll get into that. We talk about kidneys. So these are the adrenal glands. They're small. They sit on top of the kidneys. They have no connection to the kidneys. That's just where they happen to be located. And they have 3 distinct regions. Now, the first thing you notice, let me back up on that. The kidney and a number of other organs like the kidney and lymph nodes and the spleen, for example, they're going to have an outer layer called the capsule. They're all going to have a capsule. Lymph nodes, the spleen, the kidneys have a capsule. And so this is an outer covering of connective tissue. So we have a capsule on the outside here of our adrenal gland. We have a capsule on our kidneys. We have a capsule on the lymph nodes. We have a capsule on the spleen. It's just a layer of connective tissue to protect it. Underneath the capsule, we have an area called the cortex. And that is this first layer in here that we have within the cortex, we've got 3 distinct zones, but we have a cortex and a medulla. And if you look here, this dark tan area is the cortex, and the medulla is in the middle. The cortex goes from underneath the capsule to the medulla layer. Within the cortex, you've got 3 zones. You have what's known as the zona glomerulosa, the zona fasciculata, and the zona reticularis. Now, how do you know which is which? Well, you're going to have to memorize the order of them. But if you memorize the order, then when you're looking at a slide of it, if you identify the capsule, the area directly underneath the capsule is the zona glomerulosa. The medulla down here, the innermost layer, has a distinctive shape unlike anything else. So if you identify the capsule in the zona glomerulosa, if you find an area directly above the medulla, that's the zona reticularis, and then what's left in the middle is the fasciculata. Sometimes it's just memorizing which one is dark and which one's light. You know, so but you have zona glomerulosa, zona fasciculata, zona reticularis, and then the adrenal medulla. Now the medulla, of course, you heard in lecture today, releases epinephrine and norepinephrine, and it's under control of the nervous system. So yeah, but it still releases hormones, epinephrine and norepinephrine. The hormones that come out of the cortex are controlled by the pituitary gland and indirectly by the hypothalamus. So the pituitary gland tells the adrenal cortex what hormones to make. So zona glomerulosa, zona fasciculata, and zona reticularis in that order. And I know these drawings look nothing, to me, they look nothing like what we see over here. As long as you know where the capsule is, you know at least where one layer is. And that's the zona glomerulosa right underneath it. Here's a better illustration of these layers. The capsule, the zona glomerulosa, the zona fasciculata, the zona reticularis, and the medulla down here. So you should be, you know, if you can remember the order, glomerulosa, fasciculata, reticularis, and medulla, you should have no trouble identifying these. And there are three distinct types of hormones that come out. The zona glomerulosa produces one type, the zona fasciculata produces another type, the zona reticularis produces a third type. The zona glomerulosa produces what are known as the mineralocorticoids, aldosterone, regulates fluid levels, regulates blood pressure. The fasciculata releases cortisol. It helps to regulate, in addition to insulin, the hormones from the zona fasciculata helps to regulate glucose levels, sugar levels in our body. And the zona reticularis releases the androgens, the non-specific sex hormones, if you will. The androgens actually are thought to trigger the onset of puberty. And of course, down here in the medulla, we have epinephrine and norepinephrine. So here we see a really poor picture of the cross section here. This illustration is better, but here we see the zona glomerulosa releasing mineralocorticoids with aldosterone, the zona fasciculata releasing glucocorticoids with cortisol, the zona reticularis releasing the androgens, and then the adrenal medulla releasing epinephrine and norepinephrine. Okay, now this is a cross-section of a testes model, and testes are another endocrine gland, but it's also one of those mixed duty glands because in addition to it has certain exocrine functions too, because it does have a duct. The testes produce testosterone. They also produce sperm cells, and they send sperm cells out through a duct during ejaculation. So it does both. It does both endocrine and exocrine functions. We're looking at the endocrine functions now. So within the testes, we see the production of testosterone. Now these are the seminiferous tubules. Within the testes are about 1,200 or so seminiferous tubules in each testes. And in the seminiferous tubules is where sperm cells produce. Sperm cell production starts at the inside lining of this tubule, and sperm mature and move to the lumen here. These are all immature sperm cells that will eventually migrate to a structure known as the epididymis, where they will take about 3 weeks to mature. But what we're focusing on is the production of testosterone. These cells here on the outsides surrounding the seminiferous tubules are called the interstitial cells of Leydig. And they produce testosterone. So not only do we produce sperm in the testes, inside the seminiferous tubules, but we're also producing testosterone in these areas here. So the cells called the Leydig cells or interstitial cells of Leydig. Here's a seminiferous tubule. These are immature sperm being made here. These cells that produce the sperm cells are called spermatogonium. But what we're interested in right now are these Leydig cells. They're going to be producing the testosterone. And you can see how they're sort of tucked in there in between all the different seminiferous tubules. The ovary also functions as both, has an endocrine and exocrine function. Endocrine in the sense that it releases estrogen, but exocrine in that it releases, the ovary releases an ova, an egg, every 28 days or so that moves up into this uterine tube, this oviduct, this fallopian tube here, where it migrates itself down towards the uterus. So again, it is both an endocrine and an exocrine gland. So here's your ovary. Right here, all these are immature eggs that are, here we see one being released. Here's one that's ready to be released. Here is the scar from one that had been released. So each egg contains somewhere in the order of 300,000 or 400,000. I'm sorry, each ovary contains about 300,000 or 400,000 eggs. During a reproductive lifetime, perhaps only 400 or 500 eggs will get released from the ovaries. If you consider that 13 eggs or so get ovulated a year, an every 28-day cycle with a 30 or 40-year reproductive lifespan, 400 or 500 eggs tops get released. And the ovaries then secrete estrogen in addition to releasing the eggs too. Now, another structure within the ovary is called the corpus luteum. The corpus luteum is what remains after the egg is ovulated. What we see back here, there is an egg being ovulated. So this is now day 14 of the ovary cycle. Because whatever day ovulation occurs becomes day 14, because it takes 14 days then before menstruation will start. This ruptured structure here, that when ovulation occurred, becomes the corpus luteum. The corpus luteum still has a role to play here. The corpus luteum secretes another hormone called progesterone. And progesterone is what keeps the uterine lining attached in the uterus. The stratum functionalis, the endometrial layer of the uterus, called the stratum functionalis, that layer is held intact by the presence of it's bound. The stratum functionalis is bound to the uterus thanks to the role of progesterone. When if ovulation occurs but implantation doesn't, then the corpus luteum will start breaking down. And when it breaks down, it'll stop secreting progesterone, which will no longer stimulate the progesterone receptors in the uterus. And that will tell the lining of the uterus to let go and time to slough out of the uterus. This is what a corpus luteum looks like. This is an ovary that's been removed during pregnancy. Don't know why, but this was this is where ovulation had taken place. The last ovulation had taken place, and this was the structure releasing progesterone, and it will release progesterone for about the first 3 months of the pregnancy, at which time the placenta will take over producing progesterone. So, but this is what the corpus luteum looks like somewhere between release and 3 months. This is a scar from likely the month or the month before that in here. So you can see that this would have been, this what was functional, and this is what it looked like a month before, maybe 2 months before. Because there's no guarantee either that the ovaries are going to alternate left and right. They can be all left-hand side, it can be all right-hand side, it could be left, 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 right, left, left, right, right, left. Doesn't matter. Ovulation is going to occur when the ovary is ready to release the egg. When the egg's ready, it's going to get released. Okay. The corpus luteum is internally, it is a very secretory structure. It's designed to release lots of progesterone. And so we see secretory gland shape, gland nature of its structure here, because that's what it's going to do. It's going to secrete progesterone at least for 12, 13 days after ovulation, and then stop. Maybe earlier than that. But if implantation does occur, if fertilization occurs and implantation occurs, and there's no guarantee that you're going to get implantation after fertilization, but if implantation does occur successfully, then this corpus luteum will stay active for about 3 months. And this is I mentioned this earlier in lecture. This is the thymus gland. The thymus gland is located in the mediastinum. That's the middle portion of the thoracic cavity, directly above the heart. As adults, our thymus glands are pretty small because they don't have much of a role to play anymore. They still have some role, but not much. And they're designed as part of our function as part of our immune system. The thymus glands didn't actually ever secrete hormones that have an action on us. What the thymus gland did was allow lymphocytes, white blood cells that migrated there early in life, to become immunocompetent. In other words, they became trained to recognize foreign substances, pathogens, bacteria, viruses, funguses, diseased cells, any kind of transplanted tissue, any kind of foreign substance. And so the thymus gland then trained these T cells. They're called T cells or T lymphocytes, T for thymus. And as these cells matured and then went through cell mitosis and cell division, that immunocompetence was carried on to the next generation, and next generation, and next generation. So we kept these T cells present as a memory in our blood, so that whenever we're exposed to a pathogen and we respond to it, we can respond again and again and again at a much more powerful rate. We'll talk a lot about that in the immune system. So this is where T lymphocytes learn to become immunocompetent and recognize foreign substances so they can attack them and kill them. B cells, the B lymphocytes, became immunocompetent in the bone marrow. They produce antibodies for us. And the B cells are called that because of the bone marrow. So lymphocytes, white cells that are involved in our infection response and our immune response, T lymphocytes, B lymphocytes. And the thymus gland looked like this. Now it's probably even smaller. Highly secretory, but not releasing a lot of hormones out in the body. most of its action, all of its actions taking place internally where the T cells and have gone to mature. So very distinctive shape, highly secretory structure. And that is the end of AP2 lab for today. I said it would be a short lab. I thought I didn't know if I could actually stretch it out till 2 o'clock or not. So anyway, but that is the endocrine lab portion. Next week, we'll take a look at reproductive structures. We'll see some of these slides again, since a lot of them do double duty here. And then we won't have lab on Labor Day, which I think is the 6th of September. So anyway, so I will get this processed and then get this posted to YouTube later on today. Anybody have any questions? I will say that expect most of your AP2 labs to be about like this. We may go longer. There'll be a couple that may go longer, but this should be about the average amount of time. So, okay, if there are no questions, I want to go ahead and end it. Thank you for coming. Thanks for a good first day, and I'll see everybody in lecture on Wednesday.